Hey everyone, thank you for having me here. Yeah, I'm Shahar, I'm from Starkware. I'm working on the new prover called STWO. Apparently not everyone knows that, but Stone is Stark 1 and STWO is Stark 2. So this is our naming scheme. I'm working on it together with the rest of the team, with Shahar there in the crowd. We are both Shahars, working on the prover. And I want to share with you today what we got so far. STWO is an open source prover. Uh, I'll share the numbers in a bit. Okay, so first of all, what are Starks? It's a protocol for computational integrity. It means the prover has some computation. He wants to prove for another verifier. Uh, and the goal is that the verifier will have to do a lot less work than the computation itself, something logarithmic in size. So the prover generates a short proof for this computation, and the time it takes it is quasi-linear, which means like a bit more than the computation, and how much more is like something we want to optimize. And in Stark, it's something like n log n. And then the verifier can take this proof and runs this algorithm, and if it gets true, then the proof is great, and the computation is probably correct. And yeah, our goal is to make this prover as fast as possible on consumer hardware. Now, just want to mention that this is not always the goal in these systems. A lot of times it depends where you want to optimize for other stuff, like the verifier, or verify for applications when you want the proof to go on-chain, for example. But with recursion, and specifically for our case, we really want the prover itself to be as fast as possible. So this is what we focus on. And again, when I do some comparison, not everyone focuses on that. This is our focus. So STWO, what's new in STWO over Stone? STWO uses a small field, the M31 field. For that, he needs circle Starks, which is a new kind of Stark that we invent along with Polygon 0. It has GKR lookups, which are optimizing our lookups, mixed degree trace, and improved Cairo VM. All kinds of stuff. All the new stuff we know how to do, like from the last few years, we put in this prover. It's open source. It's kind of fast. It has this new circle Starks that I presented yesterday, if you want to see, on the ZK Summit, along with Ulrich. Nice thing about our prover is that it has a modular backend. It means you can take it as is and just take this directory that implements all the common operations and implement them like on GPU or other hardware, or in our case on AVX, and makes all the proof inside this backend. So if you want to try to see how efficient it is in your hardware, then you can just take it, it's open source, implement these operations, and you're good to go. And obviously, this will be integrated into StarkNet. So everyone using StarkNet will get all of these benefits eventually. All right. So how does one make a fast Stark or fast Stark prover? Well, there are a few ingredients you need to take care of. First of all, there are a lot of field and hash operations in the algorithm itself. So we want the fastest field and hash we can get our hands on. We obviously need fast hardware to run all of these hashes and field operations. We want all these math tweaks to perform less field operations and hash operations overall. We can do it using simple tweaks like a small blow-up factor, which is a trade-off between the prover and verifier. And again, we want the prover to be as fast as possible. All kinds of new algorithms like GKR, and we want efficient circuits, very small circuits and arithmetizations, and want good memory access on the hardware. And we don't optimize for the verifier, I said it a few times. So first of all, the field. What's interesting about this field we are using? The field is the Mersenne 31 field. As you can see, it's 2 to the 31 minus 1. And because the form is so simple, the operations are very fast. It was first suggested by Polygon Zero a few ZK summits ago. And we thought it was very nice, especially on CPUs and GPUs, because all of them has native support for Int32 operations. So you can do a lot of nice tricks on them. The problem was that M31 wasn't star compatible. That's why we invented, again, along with Polygon Zero, the Circle Starks, which make us be able to use it and get a very fast prover. Okay, what about the hashes? Well, a lot of projects use algebraically friendly hashes or Stark friendly hashes because we want the verify to work less. There are all kinds of Poseidons usually. We don't do that. We just take the fastest hash we can possibly take, which is like Blake 2S is one of the fastest ones there are. So we take it. Also possible to take Blake 3, which is just Blake 2 with less rounds. And you get very good performance out of it. Okay, now I want to talk specifically about the hardware. There are nice things you can do on GPUs, but we focused on AVX, because AVX can be found on consumer hardware and servers, and we can squeeze out a lot of performance from it. So on AVX 512, M31 FFT Butterfly takes like less than a cycle per one. It's it's very small. We can do like gigabytes per second of these FFTs. Blake 2 also takes like very small number of cycles. It's again fastest we know, also gigabytes per second. And these are just the performance on our AVX backend. So it's easy to replace everything else, and we do intend to do that. We intend to also implement a GPU backend, and we hope it will be very fast, but we don't know yet. And again, about the algebraic tricks. We use a blow-up factor of 2. This is the trade-off between prover and verifier. Other conservative choices like STWO or other projects may use things like 8 or 16. This is a direct multiplier of the prover, so we choose the smallest one possible, which is actually a bit less than 2. Right now we use 2, but we can actually go a bit lower than that, as also proved, planned for the future. Another thing we used is GKR lookups. From our test, they're about 2 to 3 times faster than just a regular proof of lookups, especially when done on AVX. And we have new circuits we're working on, and these circuits that take advantage of these cheap lookups that we get with GKR. And using this, we get circuits that are very small. For example, compared to other circuits we have in Stone or in other projects that might have something like 60,000 cells, 50,000 cells. We use only 4,000 cells plus a lot of lookups for Blake, which you can compare it to about 8,000 regular cells if you want to compare it to cells with no lookups. All right, so these are what we did to make STWO faster. I want to talk about the benchmarks and some comparison. Now, okay, so this is a warning slide. A lot of warnings, mainly because an apple-to-apple comparison between provers is not really possible, very hard. I sell for oranges and cherries instead of apples, but okay. Provers Okay, we chose Prover over Verifier. Not every project does that. Everyone has different hardware targets, and comparing different hardwares, it doesn't give a lot of information. The numbers don't reflect anything, obviously, so take it with a grain of salt. I can't guarantee that everything I collected on my laptop and product team's laptops because they have Macs. And the main purpose here is just to get this final metric number, is how many hardware-friendly hashes we can do per second. Okay. So, I don't know why the first one is there. Okay, so we'll start with Stone, our older prover. He has blob 16. He uses a big field, felt 252. The commitment hashes he uses are a combination of Blakes and Poseidons. I ran it on my laptop, and it proves Ketchaks. Circuit size is 70,000. Anyway, the number it gets at the end is 3.5 hashes per second. This is how much we get for Stone on my laptop. Next one on the list I compared is a Bojum. Again, it has like a slightly better blow-up factor, a lot better field, and it gets like 32x on Stone. He proves SHA 256. Next is Plunky 3 using Baby Bear, which again is not the new thing they're working on. The current one, Plunky 3, does about 700 Ketchaks per second. So this is like an improvement of the entire community. The risk 0, I tried to collect all the numbers. I'm saying on metal, it does about 1,300 hashes per second, which is like a huge multiplier already over all of the rest. And fresh one that I didn't get to put in my slides yet, because I saw it on a tweet yesterday from a Polygon Zero team. They're doing something like 2,500 Ketchaks per second. All right, so now I'll show this. This is Stone. And now, take note that this is not publicly available yet, because we didn't publish the circuit yet. So this is my estimations on my laptop. First of all, note that we use a blow-up factor of 2, which is very small. We use M31 using Circuit Starks. We use Blake's commitment hash, which means that the verifier will have a harder time proving this. And we prove the Blake hash, which you can get a very small circuit for it. Overall, we get something like 20,000 hashes per second to prove, which is more than other things I've seen right now. But I expect that other people will probably get to these areas soon as well. So, yeah. What about the verifier? Okay, right now I said I'm optimizing for the prover and screw the verifier, but we still need to do recursive proofs. So first of all, note that the verifier is still sublinear. So the question is just how big should the first proof be in order for the verification to be performant enough. The verification proof needs to be smaller than the first proof we have. So this is the parameter this affects. Verifier we estimated to need to do about 20,000 hashes, which are all Blakes right now, could be optimized. So that means a recursive proof for this kind of provers would take 1 second. That means we need to do the first proof to have lives that take more than 1 second, maybe 3 or 4, then you just start paying off. And do note that if your use case is different, you don't have these big leaves, you can take trade-offs like getting a higher blow-up factor, using a Stark-friendly hash. but I think these kind of things make sense for a lot of applications. We want to also add ZK. We plan on adding a backend for maybe WebAssembly and have ZK client-side proving. We'll see about that. All right, so that was everything. If you have a question about STWO, welcome to ask me. This is the link to the repo. It's open source. You can look at it today. Thank you very much.
Thank you, Shahar. Anyone have any questions? We can take 1 or 2 questions from the audience. Hey, can someone pass the mic, please?
Thank you. Great presentation. I was just wondering, what was the decision-making process behind GKR lookups versus like logup or CQ?
Okay, first of all, it's independent of logup or not. It is using logup. The issue, when you have logup, you need to add 4 trace cells for each logup. And we want to save these 4 trace cells because they can be very expensive. For example, in a circuit that you can see, we have like 4,000 cells plus 1,600 lookups. If each one took 4 cells, we have like more than half of the entire trace spent on lookups. So we want to do it faster, and GKR gives us that. It can do it like about 3 times faster than just using cells. So instead of like 64, I can't compute, but it's 3 times better on the lookup side. That was the thought behind it. All right.
Anyone else? Oh, please.
Thank you for the presentation. I saw you plan to use a blow-up factor of 1.5. I was wondering if you need some kind of, if there will be some research, theoretical research along it, because it sounds complicated.
No, it's actually very simple. I called it 1.5. It's not actually 1.5. It's pretty simple. You know, in Starks you have your quotient. The numerator is usually of in our circuits of degree 2. So that means we need to evaluate it on like 2n values. But if we the denominator also gets to degree n, it means the constraint holds on everything, then the whole thing shifts from 2n to just n, and we just need n points for the computation. And it also means we need to use systematic codes for the commitment. Instead of interpolating the trace and evaluating on 2 endpoints, we interpolate and evaluate on other endpoints. So instead of like 1 IFFT and 2 FFTs, we just have 1 and 1. And we use the entire thing as the committed word. That's what it means.
I see. Thanks.
Okay.
Thank you for your question. We got 1 last question here.
Okay, thank you. So I suppose that numbers you gave in the table with respect to stone are, let's say, old stone, not stone 5.
Yeah.
So I would be interested in comparison between STWO and stone 5, given the tremendous stone 5.
Stone 5.
Yeah, given the tremendous improvements in performance. I mean, just performance-wise, security-wise, and business-wise. What's from your perspective, future of those 2 provers? I mean, some kind of comparison between them.
What is Stone 5?
That's Starknet's prover on the Starknet.
Okay, Starknet. Well, first of all, currently in Starknet the prover is not the bottleneck, but Starknet provers will be just replaced as is with STWO in the future. So nothing to worry about. Okay, everything will be.
So basically, the future of Starkware with respect to provers is STWO, definitely. Yeah. Because, I mean, Stone 5 was just recently released, like open source a few weeks ago.
Yeah. Yeah, I mean, these numbers are the numbers of the current Stone, as I know it, with proving Ketchucks. Yeah.
Thank you. Thank you, Shahar.
Thank you very much.